Around Jupiter, 4 large moons move in quiet order. One is covered in volcanoes. One hides an ocean beneath ice. One is bigger than the planet Mercury. And one sits farther out, old, dark, and heavily scarred. At first, they look like 4 separate worlds. But together, they tell a deeper story. They do not orbit Jupiter like random objects that happen to be captured. They line up in a shared plane, moving with the same basic order as planets around a star. That pattern is the clue. It suggests that Jupiter's biggest moons may have formed inside a smaller version of a solar system, a disk of gas, dust, and ice that once surrounded the young planet itself. In other words, giant planets may not just collect moons. They may build them. And now, for the first time, astronomers have measured the chemistry of a disk around a young planet-like object far beyond our solar system. It is not a moon detection, it is not proof that moons are forming there, but it may be a glimpse of the kind of environment where large moon systems begin. So this video follows one question: where do organized moon systems come from? By the end of this video, you will understand why Jupiter's 4 great moons look built rather than captured, what Webb actually measured around a young object called CT-CHAR-B, and why that observation matters without pretending it proves more than it does. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. Now, the word moon does a lot of work we never ask it to do. We hear it and we picture something orbiting something else, a pale disk in the sky, a smaller body alongside a larger one. The label seems complete, but the label tells us almost nothing about origin, and origin is where the real story lives. Think about what the solar system actually contains under that single word. The moon orbiting Earth was born from debris thrown up by a giant impact early in the solar system's history. A large object struck the young Earth, material was flung into orbit, and that material eventually gathered into what we now call the moon. A violent, specific event. A one-time catastrophe. The moon carries the chemical signature of that event. It is depleted in iron, chemically similar to Earth's mantle, shaped by the specific mixture of materials that a collision between 2 young rocky planets would produce. Phobos and Deimos, the 2 small moons of Mars, look different. They are irregular, dark, cratered rocks. The leading explanation for objects like them is capture, a small body passing close enough to a planet to be pulled into orbit, rather than continuing on its way. Not built there, trapped. Think about what capture actually requires physically. A body drifting through the solar system on its own trajectory has a specific energy, a combination of its speed and its distance from the Sun. For a planet to grab it permanently, something has to reduce that energy. Atmospheric drag can do this. A collision with existing material can do it. A gravitational interaction with another nearby body can do it. But in practice, clean captures are uncommon. Most small bodies that approach a planet swing around its gravitational influence and exit the other side. The ones that stay are the ones that arrived with just the right combination of speed and direction, and then lost energy at a critical moment. Capture is not a factory, it is a net with wide holes. Now look at the moons of the outer solar system. Jupiter alone has nearly 100 known moons. Most of them are small, irregularly shaped, orbiting at odd angles, some of them in the opposite direction from Jupiter's own rotation. Captured objects, most likely, asteroids or comet nuclei that crossed too close and stayed. Neptune's large moon Triton is an extreme version of the capture story. It orbits Neptune backward, retrograde, in the opposite direction from Neptune's spin. That is a capture signature. Triton arrived from outside, probably from the Kuiper belt, captured by Neptune's gravity in an event violent enough to disrupt whatever regular moons Neptune may have had before Triton arrived. Triton is now slowly spiraling inward, losing energy to tidal forces, heading toward its eventual fate at Neptune's tidal limit. It is not a product of construction, it is a captive. But then there are the 4 large moons we started with: Io, Europa, Ganymede, Callisto, and these look different from everything else. So here is the distinction we need to carry through the whole video. Not all moons share one origin, and for the large regular moons around giant planets, the evidence points towards something more structured than capture or collision. It points toward formation inside a disk of material that surrounded the planet while it was still growing. But let's make that concrete before we name it. Picture what it means for a moon to be regular, not just large, regular. A regular moon has a nearly circular orbit. It moves in roughly the same plane as its planet's equator. It orbits in the same direction its planet rotates. And when you have several regular moons around one planet, they tend to form a kind of orderly family, distributed across a range of distances, with compositions that shift systematically from inner to outer. That kind of pattern does not emerge from random capture events. A captured body comes in at whatever angle fate gives it. A body born from an impact inherits the chaotic geometry of the collision. But a body that formed inside a disk of material around a growing planet, that body inherits the disk's geometry, flat, ordered, moving in step. And so we can use origin as a sorting tool. We are not trying to classify moons for the sake of a catalogue. We are trying to hear what the pattern is saying. If the architecture is orderly, the process that made it probably had order in it. If the composition shifts smoothly from one moon to the next, the environment that produced them probably had a smooth structure. Look at the solar system with that question in mind, and the large regular moons of the giant planets stand out immediately. Jupiter's 4, Io, Europa, Ganymede, and Callisto are the most familiar case, but Saturn's major moons tell the same kind of story. Titan is Saturn's largest moon, bigger than Mercury, with a thick nitrogen atmosphere and organic chemistry on its surface. Rhea, Tethys, Dione, and Enceladus are the other large regular moons of the inner system, all orbiting in Saturn's equatorial plane, in the same direction Saturn rotates, in nearly circular paths. Saturn also carries more than 100 smaller irregular moons in chaotic orbits, tilted, retrograde, clearly captured. The contrast between Saturn's regular inner family and its irregular outer population is one of the clearest natural demonstrations that different origins produce very different architectures within the same planetary system. Uranus shows its own version. Miranda, Ariel, Umbriel, Titania, and Oberon, Uranus's 5 large moons, all orbit in Uranus's equatorial plane, which is itself dramatically tilted relative to the planet's orbital path. Uranus was knocked on its side, probably by a giant impact early in the solar system's history. The regular moons share that tilt, meaning they formed after the tilting happened, inside a disk that had already inherited the new geometry. They are regular relative to Uranus as it actually is. So the category of large regular moon around a giant planet appears consistently across the outer solar system, at Jupiter, Saturn, and Uranus, in different environments, around planets with different mass and different histories. That consistency points toward a common underlying mechanism. We need one more distinction before we move on. We can talk about disk-borne regular moons without claiming that every detail of how they formed is settled. The broad idea that large regular moons grow inside planet-centered disks is widely supported. The specific pathways, the seed sizes, the exact role of gas drag and solid delivery, the conditions under which moons survive migration, those remain active areas of research. So we are carrying two things at once, a strong general picture and honest uncertainty at the edges. Now here is the consequence of that for everything that follows. We are going to use Jupiter's large moons as our local evidence, and we are going to use a distant young system observed by Webb as our modern test case. Neither of them proves everything. Together they reveal a consistent story. Giant planets can gather disks, and those disks can build the moons we actually see. But to hold that story properly, we have to start by understanding what it means for a moon to be architecture rather than accident. Here is a useful way to feel that distinction. Think about what the solar system would look like if all moons were purely accidental. We might expect a random scatter of sizes, compositions, and orbital inclinations around each giant planet, some moons tilted at unusual angles, some racing in opposite directions to the planet's spin. Little consistent relationship between them. No orderly chemical gradient, no resonance chains. just the historical record of whatever happened to wander close and get caught. That is not what we see around Jupiter, Saturn, or Uranus. The regular moons of those planets, the large ones that formed nearby, are flat, orderly, and compositionally graded. The irregular moons, objects that probably were captured later, are the ones that appear tilted, retrograde, and compositionally random. The distinction between the two populations is visible in the data, and the regular population is precisely the one that disk building theory is designed to explain. So when we say moons can be architecture, we are saying something specific. We are saying that the same process that formed the giant planet also organized its satellite system, printed a chemical gradient into it, and locked its inner members into orbital rhythms that persist today. That is not a loose analogy. It is a claim about formation physics that connects what we can measure now to a process that ended billions of years ago. And we are just beginning to see what that difference looks like when we can observe a living example of the construction rather than just the finished building. Now, let's look at Jupiter's 4 large moons as if we are seeing them for the first time. Not as names in a textbook, not as familiar targets for spacecraft, but as a physical arrangement that needs to be explained. Io is the innermost. It sits about 420,000 kilometers from Jupiter's center. Europa is next, at about 670,000 kilometers. Then Ganymede at just over 1 million kilometers, and Callisto at the outer edge about 1.9 million kilometers out. Look at those distances and notice what they are not. They are not random. They are not scattered at arbitrary intervals. They form a sequence that extends outward with a kind of measured spacing. Not perfectly even, but ordered. Systematic. Now look at the orbits themselves. All 4 move in nearly circular paths. All 4 orbit in roughly the same plane, roughly the plane of Jupiter's own equator. All 4 move in the same direction Jupiter rotates. The whole system has a coherent geometry, as if someone laid it out on a flat surface and adjusted the distances until the spacing satisfied some constraint, and 3 of the 4 are locked into a resonance. Io completes 4 orbits for every 2 completed by Europa. Europa completes 2 orbits for every 1 completed by Ganymede. The ratios are 4 to 2 to 1. This is called the Laplace resonance, and it means these 3 moons are gravitationally entangled, each one pulling on the others just enough to keep the rhythm locked in. That resonance is not a coincidence. It is evidence of a long history of gravitational interaction inside a structured environment. Resonances of this kind do not survive in a random collection of captured bodies. They require moons that formed and evolved together in a shared disk close enough to interact, over long enough timescales to lock into stable ratios, and the resonance is still working. The gravitational interaction between Io, Europa, and Ganymede is not just a historical record, it is an ongoing engine. Because the resonance forces Io's orbit to remain slightly elliptical rather than perfectly circular, Io is constantly being flexed. As it moves around Jupiter, its distance from the planet changes slightly, which means the tidal force Jupiter exerts on Io changes slightly. That changing tidal force squeezes and stretches Io's interior, and the friction from that squeezing generates heat, enormous amounts of heat. Io is the most volcanically active body in the solar system because of the orbital resonance that formed when the Galilean moons settled into their current configuration. The formation history of the Galilean system is not just past, it is present, still operating, visible on Io's surface every time a volcano erupts. So the architecture already tells us something important. The Galilean moons look like they grew in an ordered environment and settled into their current arrangement through a process governed by physics, not one governed by chance, but the composition tells us even more. Io is the closest to Jupiter, and it is dry, no water, intensely volcanic. Europa is next, and it has water, a vast ocean beneath an icy shell. Ganymede has water ice mixed into its composition. Callisto is the most primitive looking of the 4, darker and heavily cratered, with a composition suggesting it formed more slowly and changed less than its siblings. And Callisto is not simply old-looking. It may be physically different from the other Galilean moons in an important way. Io, Europa, and Ganymede appear to have differentiated, separated into distinct layers, with a dense iron-rich core at the center and lighter rock or ice above. Callisto shows much weaker evidence for this kind of layering. Its interior may be a more uniform mixture of rock and ice, rather than a cleanly separated structure. One idea is that Callisto formed more slowly than the inner moons, accumulating material gently at the outer edge of a disk that was running thin. Fast formation heats a moon's interior and drives melting and layering. Slow formation means a cooler body that never fully separated. If Callisto formed slowly enough in a disk that was winding down as it grew, its undifferentiated interior is a thermal fossil, a record of conditions at the outer edge of Jupiter's disk as the disk itself was losing its supply. Ganymede, by contrast, shows something unexpected, a magnetic field of its own. Most moons do not have one. A magnetic field requires a conducting fluid interior that is still moving, typically a molten iron-rich core generating the field through convection. Ganymede's field is a sign of a geologically complex, differentiated body, the product of formation in a substantial disk with enough material to build something Ganymede-sized, and enough heat from formation and tidal interaction to keep its interior active long after. Now look at what the composition gradient tells us. The moons that formed closer to the young, hot Jupiter are drier. The moons that formed farther out are icier. The composition shifts with distance from the planet, just as we might expect if the moons grew inside a disk where temperature decreased with increasing distance from the central body. We see the same kind of compositional gradient in the planets of our solar system as a whole: rocky planets close to the Sun, icy and gas-rich planets farther out. The gradient reflects the temperature structure of the disk that formed them. The Galilean moons are showing us a smaller scale version of the same logic around Jupiter, and that tells us something important about how we should think about them. They are not random. They are not incidental. They are a record, a physical archive of the conditions inside a disk that surrounded a young, growing Jupiter. The arrangement carries the geometry of that disk. The compositions carry its temperature history. The resonance carries the gravitational history of how the moons settled into their current spacing. Think about what it means to call Jupiter a system builder rather than just a planet with moons. It changes the category entirely. Jupiter is not a large body with some smaller bodies attached. Jupiter is a center of organized construction that produced a structured family of worlds, each one shaped by its position in the disk, each one a record of a specific slice of conditions. And there is something else worth noting here. Jupiter's large moons are unusually compact relative to the planet. The total mass of the Galilean moons is small compared to Jupiter itself, roughly 1/10,000th. Other giant planets in our solar system show a similar ratio. Their regular moon systems are also compact relative to the central planet. Think about what that regulation implies. It suggests the disk does not simply fill up with moon material and then stop. The disk has a throughput. It receives material from outside, feeds the planet, and provides conditions for moon growth all simultaneously. The moons that grow inside it are competing with the inward flow toward the planet, with other growing bodies, and with the disk's own finite lifetime. The resulting moon systems are compact because the disk regulated their growth. The disk both built the moons and limited them. The compact mass ratio is not an accident. It is a prediction of the same disk physics that explains the flat orbits, the resonances, and the compositional gradients. So we are looking at an architecture that is orderly, compositionally graded, resonant, and constrained. Every one of those features points toward formation in a disk, but we have not yet explained how that disk forms in the first place, or what it looks like while a planet is still growing. Here is something worth slowing down on. We cannot observe that circumjovian disk directly. Jupiter is 4.5 billion years old. Whatever disk surrounded it during formation has long since dissipated, scattered by the planet's own gravity, consumed as material fed the growing giant, or blown away by the sun's radiation after the disk lifetime ended. The disk we infer from the moons lasted perhaps 100,000 years. Nothing of it remains. So how confident can we actually be that it existed? The answer is quite confident, because the moons are a strong constraint. Detailed modeling of Galilean satellite formation shows that the architecture we observe, the spacing, the resonance structure, the compositional sequence, fits the predictions of circumplanetary disk models well. The model in which moons grow slowly inside a gas-starved, continually replenished disk produces outcomes matching the observed system better than alternatives that do not invoke a disk at all. And the resonance chain carries additional weight because it is not easily produced by capture or impact. Gravitational resonances between moons in a shared disk environment can lock in during formation and persist for billions of years. The Laplace resonance among Io, Europa and Ganymede is a fossil of exactly that kind of shared formation environment. But knowing the Galilean system argues for a disk, and knowing that disk is long gone leaves us with an obvious challenge. If we can only infer the disk from the moons it built, how do we test the mechanism directly? And that is what we need next. Now here is the picture we need to hold. A giant planet is not born fully formed. It grows, and while it grows, it feeds material from the surrounding nebula, gas and fine solid particles, falls inward toward the planet. But that material does not fall straight down like rain. It has sideways motion, angular momentum, and angular momentum changes everything. Imagine spinning a bucket of water over your head. You can keep it moving in a circle, but you cannot easily stop it without the water going somewhere. The water has angular momentum, which means it resists collapsing straight inward. It wants to spread out into the path of least resistance, a rotating structure, a disk. That is what happens when material with sideways motion falls toward a growing planet. It cannot fall straight in. It arrives from different directions, different speeds, different angles. The competing sideways motions average out into a single rotating structure. A disk of gas and solids settles around the planet, flat and circular, with the planet at the center. We call this a circumplanetary disk. The term is precise and worth knowing, but the picture matters more than the label. Think of the circumplanetary disk as the natural outcome of falling material with spin. Any time material with angular momentum falls toward a central body, a star, a planet, a growing proto-moon, it flattens into a disk if the angular momentum is too large for the material to fall straight in. Disks are the default geometry of gravity plus spin. What is remarkable is not that circumplanetary disks exist. What is remarkable is that we can now observe one. Now let's be precise about what kind of disk this is. Material flowing into the circumplanetary disk comes primarily through the boundary regions of the larger disk around the star. Close to the planet's gravity has influenced the surrounding nebula, creating a gravitational sphere in which the planet dominates the local dynamics. But material flows across this boundary through streams, drawn inward by the planet's pull, and falls into the circumplanetary disk from above and below the disk plane, as well as from the outer edges. The geometry is complex, not a simple drain, but a three-dimensional infall shaped by the planet's mass and the surrounding disk structure. The disk around a star, the one our solar system's planets formed inside, is called a protoplanetary disk. It is enormous, spanning hundreds of astronomical units, rich in gas and long-lived. A circumplanetary disk is different. It is much smaller, centered on the planet rather than the star, and supplied by material flowing in through the larger disk. Think of it as a sub-disk inside a larger disk, a disk within a disk. And here is what makes it interesting. The circumplanetary disk serves two jobs at the same time. The first job is delivering material to the growing planet. Gas and solids flow inward through the disk toward the planet's surface, feeding its growth. Jupiter's enormous mass required an enormous amount of incoming material, and the circumplanetary disk was part of the channel that delivered it. The second job is being a potential moon-building environment. Not all the material makes it to the planet. Some stays in orbit within the disk, some cools and collects, some begins to stick together. And this material, the part that lingers in orbit rather than falling in, is the raw stock from which large regular moons may have grown. Now, here is a concept that matters deeply for what kind of disk this actually is. A disk that is supplied rapidly is gas-rich and relatively massive. Gas-rich disks exert strong drag on forming solid bodies, which means strong migration forces pushing forming moons inward. A disk that is supplied slowly, a gas-starved disk, is thinner, less massive, and gentler on forming moons. The classic picture of how Jupiter's moons formed, developed by Robin Canup and collaborators, argues that Jupiter's circumplanetary disk was gas-starved for much of the moon-building phase. The planet's late accretion was slow, and the disk never built up to the densities that would have driven all the forming moons inward before they could survive. In a gas-starved disk, solid material can accumulate relative to gas as the disk evolves. Solids are delivered continuously as captured small bodies, as particles filtering in from the outer nebula, while the gas supply tapers. Over time, the ratio of solids to gas in the disk can increase, providing more raw material for moon seeds even as the migration threat diminishes. And the temperature structure of the disk is also critical. Near the planet, the disk is hot, warmed by the planet's own radiation and by the energy released when material falls inward. Farther out, the disk cools. Different materials condense, freeze from gas into solid particles, at different temperatures. Water ice condenses at relatively low temperatures, which in Jupiter's circumplanetary disk meant somewhere beyond a specific distance from the planet. Rocky materials that are made of silicates and metals condense at much higher temperatures and are solid throughout the disk, even close in. This radial temperature gradient sets a chemical structure, a set of frost lines or snow lines, that determines what solid material is available at each distance, and those snow lines are preserved in the moons that formed at each position. Io, close in and dry, formed inside the water snowline. Europa, with its deep ocean beneath ice, formed outside it. Ganymede and Callisto, richer in ice, formed farther out still. The composition of each Galilean moon is a geological record of where in the disk it formed and what the temperature was at that position. The disk is not just a construction zone, it is a chemistry factory, sorting material by temperature into distinct zones and building moons with distinct compositions from each. But we need to be careful about how we picture this disk overall. It is not a neat, ordered structure sitting quietly around Jupiter. It is turbulent, evolving, and temporary. Material flows in from outside. Material flows inward toward the planet. The disk changes over time. In the earliest phase, when Jupiter was actively accreting its gas envelope, the circumplanetary disk was at its most active, most material flowing, most turbulent, most gas-rich. As Jupiter's accretion slowed, the disk thinned. The supply from the outer nebula diminished. Gas began to dissipate. The migration environment changed. The disk at 10,000 years of age was a very different structure from the disk at 1 million years of age. Think of it less like a smooth ring and more like a river system, constantly supplied from upstream, constantly draining toward the planet, with complex currents throughout. And embedded in that river, possibly growing in the calmer regions, possibly forming in resonant zones, possibly being swept inward and lost, moon material. Now here is one more thing to notice. The same basic physics applies whether we are talking about a giant planet forming inside our solar system 4.5 billion years ago, or a young planetary mass object somewhere else in the galaxy today. Angular momentum is universal. When material with sideways motion falls toward any massive growing object, a disk forms. The scale and details vary, but the basic structure is the same. So when we later look at a young system outside our solar system, where a planet-like object appears to have a disk of its own, we are seeing the same physical logic playing out. Same driver, potentially the same result, but the result, actual moons, requires more than just a disk. It requires the disk to deliver the right material, in the right conditions, over the right timescale. And even then, it requires the moons that form to survive long enough to still be there when the disk is gone. Think about what the disk lifetime problem means for the outcome. A circumplanetary disk is not a permanent feature. It is active during the planet's gas accretion phase, and it dissipates as that accretion winds down. Moons forming inside it face a window, grow fast enough to reach a size where their own gravity dominates before the disk fades, or be stranded as incomplete objects when the material supply cuts off. Modeling of the Galilean satellite system suggests the window may be tight enough to favor a late formation scenario. Moons that form early when the disk is dense and active experience strong gas drag and spiral inward toward the planet. The Galilean moons we see today may be survivors of a final generation that formed as the disk was thinning, when drag forces were weak enough to allow stable orbits to persist. Earlier generations may have been lost. The surviving generation is what we can observe. That adds a layer of contingency to the story. The Galilean system is not simply what a circumplanetary disk produces. It is what a particular disk, at a particular stage of its decline, produced under conditions that happened to allow 4 moons to survive. Different disk lifetimes or mass flow rates could produce different architectures, or no surviving regular moons at all. That is the next piece we need. Not just how a disk builds moons, but what allows moons to outlast the building process. Now, a disk is not the same as a moon. Having a rotating structure of gas and dust around a planet does not automatically produce a moon system. Something more has to happen. Diffuse material has to become concentrated. Small concentrations have to grow. Growing bodies have to avoid falling inward or colliding destructively. And they have to do all of this against a clock, because the disk does not last forever. What we are really describing is a race, and not every disk wins it, so let's follow the process in physical detail. The first challenge is getting solids into the disk in a useful form. Gas flows through the disk relatively easily, carried by pressure gradients and turbulent mixing. But solid particles are dynamically distinct from the gas. They do not feel pressure in the same way. Instead, they interact with the gas primarily through friction, aerodynamic drag. The strength of that drag depends on the particle size. Very small dust grains couple tightly to the gas and move with it. Very large boulders barely interact aerodynamically and move almost as if the gas were not there. But particles of intermediate size, pebbles roughly centimeters to meters, experience just enough drag to drift through the disk while still being large enough to carry significant mass. These pebbles are where moon-building material most efficiently concentrates. Some solid material enters the circumplanetary disk directly from the larger disk around the star. Some arrives as small rocky bodies, planetesimals, that pass through the disk environment and are captured or ablated. Think about what ablation means here. A small body entering a gas-rich disk does not survive the journey intact. Gas drag slows it, heats its surface, and strips material off it. The stripped material, now small particles moving at disk velocity, settles into orbit inside the disk. The incoming body loses material and either is captured or passes through, but it has donated solids to the disk. Those solids are the seeds. Pebbles, small solid objects roughly a centimeter to a meter in size, can also drift efficiently through the gas because they experience intermediate drag. They slowly move inward through the disk, delivering solid material from the outer disk regions toward the growing moon seeds. This process, called pebble accretion, can accelerate the growth of moon seeds substantially. A growing moon seed has gravity that pulls nearby pebbles in as they drift past. The larger the seed, the larger the cross-section it sweeps, and the more pebbles it captures per unit time. So growth is self-reinforcing. The larger the body, the faster it grows relative to its size, at least until the supply of pebbles is exhausted or migration carries the seed away from the pebble stream. Now those seeds need to grow. In the earlier picture of moon formation, associated with the work of Robin Canup and others, the disk was imagined as a relatively gas-rich environment where solid particles experience drag, settled to the disk midplane, and gradually stuck together through low-velocity collisions. Small grains became pebbles. Pebbles became larger bodies. Larger bodies swept up material through gravity. The process is called accretion, and it is the same basic process that built the planets, but more recent work has added details that change the picture in important ways. Ronnet and Johansson, working in 2020, developed a model in which moon formation inside a circumplanetary disk depends on the capture and ablation of small incoming bodies, called planetesimals. In this picture, the disk is not initially full of solids. Instead, solids are delivered continuously by incoming objects from the outer solar system. These objects arrive, lose material to gas drag, and that material accumulates within the disk. Ronnet and Johansson emphasized that this continuous delivery changes the timing and the distribution of solid material in the disk, and both of those affect whether moons can grow to a useful size before the disk dissipates. Ronnet and Johansson also flagged the importance of the incoming planet-sesimal flux for replenishment. If many planet-sesimals are being ablated into the circumplanetary disk continuously throughout the disk's lifetime, the solid delivery is roughly spread out over time rather than concentrated in an initial pulse. Moon seeds are being replenished even as earlier generations are lost. The disk is not simply running down its initial solid inventory. It is being refueled by the ongoing flux of incoming bodies from the outer solar system. Now, here is a key constraint. The circumplanetary disk is not a long-lived structure. It lasts roughly as long as it takes for Jupiter to finish its main phase of growth, and for the parent disk around the Sun to dissipate. That is thought to be somewhere in the range of a few million years. During that window, moon seeds need to form, grow, and stabilize. Any body that grows too slowly or in the wrong part of the disk may not make it. And here is another constraint. Gas drag works against moon survival as well as for it. Growing bodies inside the disk exchange angular momentum with the surrounding gas. This exchange causes them to migrate, to drift inward toward the planet. Small bodies migrate faster. Large bodies migrate more slowly, but they still migrate. So there is a race. Can a moon seed grow large enough, quickly enough to survive the inward drift? In regions of the disk where there is a local pressure maximum, a bump in the gas pressure profile, solid particles can become trapped rather than drifting inward. These pressure bumps act as collection points where solid material accumulates. Moon seeds that form at or near a pressure trap may grow faster than average, which partly explains why Jupiter's large moons are not uniformly spaced. They exist at specific locations rather than being spread continuously through the disk. And here is how resonant chains connect to all of this. As forming moon seeds reach sufficient size, they begin to interact gravitationally with each other and with the disk. Under the right conditions, a more massive outer moon can gravitationally slow a growing inner moon, reducing its inward drift. The inner moon is captured into a resonant relationship with the outer one. Both moons then migrate together, more slowly than either would migrate alone. Add a third moon growing farther in, and a resonant chain can form, a family of moons locked into harmonic ratios, collectively resisting the disk torque that would push each one individually inward. Canup's work on the circumjovian disk emphasized that the gas-starved condition was important precisely because of this tension. In a gas-starved disk, the migration rate is slower, which means the race between growth and loss is more winnable for forming moon seeds. Canup's models suggest the surviving Galilean moons contain roughly the amount of solid material that would have been delivered through Jupiter's disk during the late accretion phase, consistent with the observed compact mass ratio. The total mass of the Galilean moons is not just an incidental fact, it is a tracer of how much solid material flowed through Jupiter's circumplanetary disk over the entire formation phase. The Galilean moons are a measurement of a physical quantity, total solid throughput, that we cannot otherwise access for Jupiter's formation history. The gas-starved picture helps here. If the disk is not too dense, migration is slower. If solid delivery is spread over time, moon seeds have a longer window to grow before they reach a dangerous size regime. But the picture is still one of constant tension. Formation and loss are happening simultaneously. Moons are being built and destroyed in the same environment, by the same physics at the same time. So the Galilean moons we have today are not simply the moons that formed, they are the moons that survived. And here is what that survival filter means for what we actually observe. If multiple generations of moons formed and were lost before the current generation stabilized, then the Galilean system is not a record of typical disk-built outcomes. It is a record of one specific outcome, the one that happened to survive under the conditions that prevailed during Jupiter's late accretion phase. Different disk properties might have produced different final architectures, or no stable regular moons at all. The system we see is one draw from a distribution of possible outcomes, not a guaranteed result. That is a sobering thought, but it is also a scientifically useful one. It means that studying circumplanetary disks across a range of ages, masses, and separations is not just about confirming the basic theory, it is about mapping the space of possible outcomes. What disk properties favor moon survival? What disk lifetimes produce stable resonant systems? What mass ranges produce moons that stay in tight orbits versus spread out? These questions require a sample of systems, not a single case, and surviving the disk is a different problem from forming inside it. Now, building a moon is the easier half of the problem. Keeping it alive is where things get complicated. A growing moon inside a circumplanetary disk is constantly exchanging momentum with the gas around it. That exchange has a name: disk-driven migration, and its most natural result is inward drift. A moon that forms at a comfortable distance from Jupiter does not simply stay there, it moves. Let's make this physical. Think of it as an asymmetry in the gravitational pull. The gas just outside the moon's orbit is moving slightly slower than the moon. It is farther from the planet, and thus moving at a lower orbital speed. The gas just inside the orbit is moving slightly faster. As the moon moves through this structure, it interacts gravitationally with both the inner and outer gas, but the interactions are not symmetric. The net effect is a small but persistent drag that pulls the moon's orbit inward. Imagine a growing moon orbiting inside the disk. The gas ahead of it in its orbit is slightly denser and closer than the gas behind it, because the moon disturbs the disk structure as it moves. That asymmetry means the disk pulls slightly harder on the moon from ahead than from behind, which translates into a net force that reduces the moon's orbital energy. Lower orbital energy means a smaller, faster orbit, closer to the planet. The moon drifts inward, the disk replenishes the asymmetry, and the drift continues. For a very small moon seed, this happens quickly. Small bodies have weak gravity and low inertia. The disk torques are relatively large compared to their orbital energy, and they spiral inward fast. Most small moon seeds probably never become moons at all. They migrate into the planet before they can grow. For a larger, more massive moon, migration is slower. The moon grows faster than it drifts, at least for a while. But even a substantial moon is not safe indefinitely. If the disk lives long enough, even large moons can migrate significantly. The distinction between large and small body migration involves two regimes. In the first regime, relevant for smaller growing bodies, the disk torque dominates and the body spirals inward relatively rapidly. In the second regime, relevant for larger bodies that have grown massive enough to open a partial gap in the disk, migration slows because the body has modified its local environment. The gap changes the structure of the disk around the migrating body, altering the torque balance. The Galilean moons, as they grew, likely passed through both regimes. In early stages, they were small and fast migrating. At some point, each grew large enough to transition into a slower migration regime. The fact that they exist is proof that at least one generation managed that transition, and here is where the Galilean moons become a clue to what happened. The work by Robin Canup points toward a picture in which Jupiter's disk was not a one-time supply, but a slowly replenished, gas-starved environment. In a gas-starved disk, migration is suppressed because the disk is less massive. Moons can grow to substantial sizes before the migration torques overwhelm them. And crucially, if the disk supply tapers off gradually, the migration environment changes over time. But even this does not guarantee survival for all the moons that form. Think about this possibility. The disk builds a generation of moons. They grow, they migrate, they approach the planet too closely. Perhaps they are disrupted by tidal forces. Perhaps they are absorbed. The disk continues to be replenished, and a new generation of moons begins to form. Those moons go through the same cycle, generation after generation. The moons we see today around Jupiter may be the final surviving generation, the bodies that formed late enough, or grew quickly enough, or happened to form in a region of the disk where migration was suppressed, or caught the disk just as it was dissipating and the migration forces were fading. Callisto is particularly interesting in this context. The CANUP models specifically flag Callisto's slow formation as meaningful. The accretion timescales needed to explain Callisto's undifferentiated structure are on the order of hundreds of thousands to millions of years, much longer than the dynamical timescales that would produce rapid heating. This is consistent with a disk that was running thin and slow by the time Callisto was growing. A disk in its final phase, with material supply dwindling and accretion gentle. Callisto's geology is a record not just of the outer disk, but of the disk's end state. It formed slowly, in a winding down environment, and its interior preserved that history in the form of mixed rock and ice rather than separated layers. Now there is a related piece here involving resonance. Io, Europa, and Ganymede are locked in the Laplace resonance today. But resonance is not something they were born into. It is something they evolved into through gravitational interaction over millions of years. As moons migrate, they can pass through resonant configurations. If the migration is gentle enough, moons can be captured into resonance, pulled into a stable ratio, rather than passing through it. The timing of resonance capture requires specific conditions. As a moon migrates inward and approaches a resonant position with a moon already in a more stable orbit, the outcome depends on the migration speed. If the migration is too fast, the moon passes through the resonance without being captured. If it is slow enough, the resonance can lock in. The outer moon pulls the inner migrant gravitationally, slowing its approach. And if the geometry is right, the two bodies settle into a stable harmonic relationship. The Laplace resonance required Io, Europa, and Ganymede to have migration histories gentle enough for two successive resonance captures to occur. That degree of gentleness points again toward the gas-starved disk picture. Enough gas to drive migration, but not so much that the migration was too fast for resonance trapping. The Laplace resonance may be a fossil record of the migration history of the three inner Galilean moons, and a constraint on the disk conditions that allowed it to form. And here is the bigger picture those models are pointing toward. Jupiter's moon system is not just a natural byproduct of having a large planet. It is a solution to a difficult physical problem. Material had to be delivered to the disk, solids had to stick together, bodies had to grow faster than they drifted. The disk had to dissipate at the right time, resonances had to lock in at the right migration speed. The surviving architecture carries the statistical signature of what the filter was. Not randomly selected from all possible configurations, but biased towards the configurations that could survive the specific conditions in Jupiter's circumplanetary disk. We are not seeing all the moons that ever formed around Jupiter. We are seeing the result of an extended selection process. A moon system is not an ornament, it is a survivor. And that survivor status is what makes the Galilean moons interesting, not just as objects, but as data. The arrangement we see today is the arrangement that passed through the filter. It carries the memory of what the filter was. Now we can ask a harder question. If this is what a moon system looks like after the construction site has cleared, ordered, resonant, compositionally graded, compactly surviving, then what does the construction site itself look like while it is still running? Now this question has been central to the field for decades. We can work backward from the finished architecture. We can build models of what a circumplanetary disk must have looked like to produce the Galilean system. But working backward is not the same as looking directly. Every inference from the Galilean moons to the disk that built them is exactly that. An inference constrained by the outcome, not a measurement of the process itself. What the field has needed is a direct observation of a circumplanetary disk while it is still present. A young system, early enough that the disk has not yet dispersed, with material still available to characterize. A live construction site rather than a 4 billion-year-old archaeological record. The difficulty is real. Such young systems are rare at any given moment. Circumplanetary disks are faint. The companion they surround is bright. The host star is brighter still. Separating disk signal from the surrounding noise requires unusually favorable geometry or an instrument with sensitivity that simply did not exist until recently. So the survival question and the observational question converge. To understand what conditions allow moon systems to form and persist, we need to study disks while they are active. That requires both a young target and an instrument capable of reading the disk's chemistry against the background noise. That is what we have never been able to see clearly, until recently. Now, here is the observational problem in plain terms. A circumplanetary disk around a young giant planet is small, faint, and positioned directly next to an extremely bright object. Let's put numbers on that to make the difficulty concrete. Jupiter is roughly 143,000 kilometers across. The circumplanetary disk that may have surrounded young Jupiter extended out to perhaps a few hundred Jupiter radii, a few tens of millions of kilometers. That sounds large, but compared to the distance to even the nearest star-forming regions, it is tiny. The nearest star-forming regions are roughly 140 to 500 light-years away. At that distance, the entire circumplanetary disk we are trying to observe would appear as an angle of less than 1,000th of an arcsecond. We do not have instruments that can resolve that. Camp and collaborators, in work published in 2019, explored these specific observational challenges for detecting gas in circumplanetary disks around wide-orbit companions. Their analysis showed that even for the most accessible targets, wide-separation planetary mass companions in young star-forming regions, the gas emission from a circumplanetary disk would be extremely faint. The signal would be buried under the companion's own thermal emission and the surrounding noise from the star-forming environment. To constrain the gas disk properties rather than simply the companion's atmosphere, you would need both high sensitivity and the ability to separate the disk's spectral contribution from the companion itself. That paper was written before Webb was operational. It was partly a prediction. These objects exist and matter, but the instrumentation needed to characterize their gas content was not yet available. Webb's MIRI changed the calculation. But there is a deeper problem than resolution alone. Any light coming from the disk has to be separated from the light of the host star. A bright young star can be 10 million times brighter than the material we are trying to detect in a disk around its companion. Separating the companion's disk signal from the overwhelming glare of the star requires extremely precise optical techniques, blocking the starlight, subtracting contributions from known optical artifacts, and looking for a faint residual signal at just the right position and wavelength. And even when we manage to block the star, we face another problem. The companion itself, the giant planet or planetary mass object, is also bright. Its own thermal emission competes with the emission from the disk around it. Separating the planet's spectrum from the disk's spectrum requires high spectral resolution and careful modeling. We have to know what the companion should look like without the disk in order to see what the disk is adding on top. Before Webb, what could observers actually say about circumplanetary disks around young companions? The honest answer is, not much, directly. There had been attempts to detect dust emission from potential circumplanetary disks around wide separation companions using millimeter wavelength interferometry, facilities like ALMA. In a few cases there was evidence that wide separation companions had associated dust, enough to suggest something disk-like was present. But characterizing the disk, reading its chemistry, or distinguishing the disk material from the companion's own thermal emission was beyond what those early observations could do. The field was at the stage of hints and candidates rather than confirmed direct characterizations. Liu and collaborators in 2024 work preparing for JWST-era observations modeled what the expected near-to-mid infrared signatures of circumplanetary disks would look like, and argued that JWST could distinguish between disk types based on their emission colors, the ratio of brightness at different mid-infrared wavelengths. That theoretical groundwork was part of what made the CT-CHAB observations interpretable when they arrived. The Webb team did not just point a telescope at something unfamiliar. They pointed it at a target that had been theoretically prepared for. So let's be precise about why all of this matters. If we cannot directly observe circumplanetary disks, we are limited to inferring their past existence from the moon systems they left behind. The Galilean moons are evidence that something disk-like existed around young Jupiter, but we are reading the output, not watching the process. And inference has limits. When we look at Jupiter's moon system and argue backward to a disk, we are working with a single data point. one planet, one system, one set of surviving moons. Our models are calibrated to explain that one outcome. We do not know whether Jupiter's disk was typical or unusual. We are not yet in a position to test those questions with data. To make progress, we need direct observation of disk material around a planet-centered object, while the disk is still there. And this is where something important changed in the last few years. Wide separation companions are more accessible than close-in ones. When a planetary mass companion orbits far enough from its host star, tens or hundreds of astronomical units, the angular separation is large enough that modern instruments can block the star's light and still detect the companion. And with very high contrast imaging, it may be possible to detect the disk around the companion as well. Wide orbit companions are also often younger systems, because planetary mass companions at very wide separations tend to be found preferentially in young star-forming regions where they have not yet had time to dissipate their formation-era disks. Webb changed what is possible here, but it is worth being specific about what part of Webb's capability matters most. The key is mid-infrared spectroscopy. Disk material around a young planetary mass companion is warm, heated by the companion's own radiation and by accretion processes, but it is not bright at visible wavelengths. It emits most strongly in the infrared, at wavelengths corresponding to the thermal emission of material at temperatures from a few hundred to a few thousand Kelvin. And many of the key molecular species that carry chemical information, water, carbon dioxide, carbon monoxide, simple hydrocarbons, more complex organics, have their strongest spectral features in the mid-infrared range, roughly 5 to 28 micrometers. Webb's MIRI operates precisely in this range, with sensitivity levels that were not achievable with previous instruments. Not because earlier telescopes were badly designed, but because water vapor in Earth's atmosphere absorbs mid-infrared light, making ground-based observation at these wavelengths extremely difficult. A space telescope above the atmosphere can access this window cleanly, and that means the gap between theory and observation, between the Galilean moons and the disk that made them, just became narrower. Here is why mid-infrared spectroscopy matters so much for this specific problem. The molecules that form in circumplanetary disk conditions, carbon compounds, water ice, silicate grains, emit and absorb light at characteristic infrared wavelengths. A spectrum of that material carries a chemical fingerprint. Reading that fingerprint tells us what the disk contains, which molecules are present, in what proportions, at what temperatures. That is not just detection, it is characterization. And characterization is what allows us to connect disk chemistry to the conditions under which moons could form. Before Webb, no instrument had the combination of sensitivity and wavelength coverage needed to read that fingerprint in a faint, compact disk around a distant companion. Liu and collaborators modeled what JWST-era observations might reveal about circumplanetary mass object disks, and found that near to mid-infrared signatures could distinguish disk types and constrain properties in ways that previous instruments could not access. Webb made that possible, and the first test of that capability on a young planetary mass companion with confirmed disk-like emission was about to produce results that would connect a 2-million-year-old system in the constellation Chamaeleon directly to the question of how Jupiter's moons came to exist. Now, the significance of that connection deserves to be held clearly before we move into what Webb actually found. We are not saying that CT-CHA-b is young Jupiter. We are saying that it is a system where the physics of a giant planet-scale object interacting with circumplanetary material can be studied while it is still happening. That is what makes it a bridge, not identity, but contemporaneous access to the process. The Galilean moons show us the outcome. CT-CHA-b gives us a view of the conditions that could produce it. The system that bridges that gap is called CT-CHA-b. Now, let's place CT-CHA properly in the story before we explain what Webb found there. CT-CHA is a young star in the constellation Chamaeleon, about 165 light-years from Earth. The Chamaeleon constellation hosts one of the nearest active star-forming regions to Earth, known as Chamaeleon T1 and its related subgroups. These regions contain young stars in the process of shedding their natal gas and dust, with ages estimated at around 2 million years. CT-Char is one of these young stars, a T Tauri star, which is the class name for young solar-type stars that are still accreting material and have not yet settled into the stable hydrogen-burning phase of their main sequence life. The fact that CT-Char is a T Tauri star means it is still surrounded by its own protoplanetary disk, and any companion that formed around it would also still be near the beginning of its formation history. CT-Char b is a companion orbiting CT-Char. It was discovered in 2008 and classified as a planetary mass companion, an object with a mass estimated at roughly 17 Jupiter masses, orbiting at a wide separation of about 440 astronomical units from its host star. Jupiter orbits the Sun at about 5.2 astronomical units. CT-Char b orbits CT-Char at 440 astronomical units. That is roughly 85 times the distance. At that separation, Connecticut-Char b is well outside the zone where the host star's light overwhelms everything nearby. A coronagraph, an instrument that blocks the central star, can suppress the star's glare to a level where the companion and its disk become detectable. Without the wide separation, the disk material would be drowned in stellar glare no matter how sensitive the telescope. Now, a mass of 17 Jupiter masses sits in an interesting region. Planets are typically defined as objects below the deuterium burning limit, which falls around 13 Jupiter masses. Above that threshold, objects are sometimes called brown dwarfs. CT-Char b is at or slightly above that boundary, which places it in a classification gray zone. But here is the important point about that debate. We are not going to let the taxonomy become the story. Whether CT-Char b is best described as a planetary mass companion, a very low-mass brown dwarf, or something in between is genuinely uncertain and depends partly on how it formed. What matters for our purposes is this. It is a young, giant planet-scale object with its own disk of material, in a system young enough that the disk is still detectable. The classification debate is real, and it has some implications for how the object should be interpreted scientifically. But for the purposes of moon formation, the question we are building toward, what matters is not the precise taxonomic category. What matters is whether it formed with or associated with a disk of planet-building material around it, and whether that disk has had time to progress toward moon-building conditions. On both of those questions, the evidence points toward yes, and the youth of the system is what makes it irreplaceable. There is a window for observing circumplanetary disks that is genuinely narrow. A disk around a forming giant planet exists during the gas accretion phase, and for some time afterward, while the disk material dissipates. Models suggest the disk lifetime is typically a few million years. By around 10 million years, most circumplanetary disks would be largely dispersed. Finding a young enough system to still have detectable disk material, and having that system be at the right distance from its host star to be observationally accessible, is a combination of constraints that limits the available targets severely. CT-Char b at 2 million years old is close in age to the active construction phase. The disk around it has not yet had time to fully dissipate. The material is still there, still warm, still emitting. In our own solar system, any disk that may have surrounded young Jupiter is long gone, dispersed by the time the solar system was 10 to 20 million years old. We cannot go back and observe it, but CT-Char gives us something analogous in another system while the clock is still running. Think about what this changes for the science. Previously, the evidence for circumplanetary disks around giant planets was largely indirect. We inferred their existence from the moon systems they left behind. We built theoretical models calibrated to match those moon systems, but we could not directly observe the disks themselves at the appropriate stage of formation. CT-Char is not the first system where a disk around a wide separation companion has been discussed. Before Webb, Connecticut-Char had been observed at near-infrared wavelengths using ground-based adaptive optics instruments. Those earlier observations confirmed that CT-Char had an excess of infrared emission beyond what its thermal photosphere alone would produce, a hint that something additional, probably a disk, was contributing to the light. But those observations could not tell us what the disk was made of, how warm it was at different distances from the companion, or whether the chemical makeup differed from the disk around the host star. They confirmed the presence of something. They could not characterize its nature. The step from something is there to this is what it is made of is exactly what spectroscopy enables. And mid-infrared spectroscopy with Webb's MIRI was the first time that step could be taken for CT-CHA-b. And here is something important about the way CT-CHA-b fits into the moon building story. We are not claiming that CT-CHA-b is identical to young Jupiter. The mass is probably higher. The separation from its host star is much larger than Jupiter's separation from the Sun. The chemical environment may differ, and we do not know whether the disk around CT-CHA-b will eventually produce a moon system of the kind we see around Jupiter. That would require watching the system for millions of years, which is not an option. What CT-CHA-b gives us is a case study, a live example of disk material around a giant planet analog object at the right age. We can characterize that material, we can measure its chemistry, we can compare it to what our models say circumplanetary disks should look like, and we can ask whether it is consistent with being the kind of environment where regular moons could form. Those are the right questions to ask of this data. And the point about CT-CHA-b's extreme separation is worth staying with for a moment. 440 astronomical units is not a normal planetary orbit. At that distance, even in a young system, formation by the core accretion process that built Jupiter becomes difficult to model straightforwardly. Some researchers favor a gravitational instability formation scenario for wide separation companions like CT-CHA-b, where the disk of the parent star fragments directly into a bound object, rather than building up from a core. Others argue the distinction matters less for the disk physics once the companion has formed. But notice what this means for the moon building question. If CT-CHA-b formed differently from Jupiter, it is still producing a circumplanetary disk. Whatever the formation channel, once a giant planet mass object exists within falling material, a disk can form around it. The disk physics, angular momentum, chemistry, temperature structure, responds to local conditions around the companion, not to how the companion itself came to be. So even if CT-CHA-b is not a perfect Jupiter analog in formation pathway, it is a valid analog for studying circumplanetary disk conditions. The question we are asking is, does a young planetary mass object surrounded by infalling material produce a disk with chemistry relevant to moon formation? And the answer to that question does not depend on whether the companion formed by core accretion or disk instability. We are not saying the differences do not matter. They do matter for a precise comparison with Jupiter's history. But for the first goal, observing a live disk, characterizing its chemistry, and connecting that chemistry to moon formation theory, CT-CHA-b's wide separation is an advantage, not a problem. It is what makes the disk accessible in the first place. And they are the questions Webb was built to help us begin to answer. Now, let's be very precise about what Webb did and did not find. The observations we are discussing used Webb's mid-infrared instrument, MIRI, in a medium-resolution spectroscopy mode. MIRI is particularly sensitive to light in the mid-infrared wavelength range, roughly 5 to 28 micrometers. This wavelength range is where warm gas and dust emit most strongly, and it is where many important molecules produce distinctive spectral signatures. The mid-infrared range is particularly valuable for identifying complex molecules. Simpler molecules like carbon monoxide and water have features across a range of infrared wavelengths. More complex molecules, including aromatic compounds with ring structures of carbon atoms, have their most distinctive spectral features in the mid-infrared. The reason is that these molecules vibrate at specific frequencies determined by their molecular structure, and those vibration frequencies correspond to mid-infrared photon energies. When mid-infrared photons interact with molecules in the disk, the molecules absorb or emit at characteristic wavelengths, leaving fingerprints in the spectrum that are unique to each molecule. Mid-infrared spectroscopy does not just tell you that something is warm, it tells you what the warm material is made of. It is a chemical probe, not just a heat detector. Spectroscopy means reading the detailed spectrum of light from an object, not just its brightness, but the precise wavelengths at which it is brighter or dimmer. Different molecules absorb and emit light at specific characteristic wavelengths. If a molecule is present in the disk material, it leaves a fingerprint in the spectrum. Webb's MIRI can read those fingerprints with a level of detail not previously available for targets this faint. But before any molecules could be measured, the data had to be extracted. The challenge of high-contrast extraction is worth understanding. CT-CHA and CT-CHA-b are separated by a large angle on the sky, which helps. But the bright host star still contributes scattered light across the detector. That contribution has to be modeled and subtracted carefully. And the emission from CT-CHA-b itself, the companion's own thermal radiation, has to be separated from any additional emission coming from the disk around it. This is not a straightforward subtraction. It requires detailed modeling of what CT-CHA-b should look like without a disk, based on its mass and age, so that the residual, what the disk is adding, can be isolated. The extraction is not infallible. Any residual uncorrected starlight in the detector region adds noise. Any imperfection in the model of what CT-CHA-b should look like without a disk affects what counts as excess. The team working with the data had to demonstrate that the excess they found was statistically robust, that it could not be explained away by modeling errors or instrumental artifacts. Part of the confidence in the result comes from the fact that the molecular features found in the disk spectrum are specific, multiple, and chemically coherent. It is not a single ambiguous excess at one wavelength. It is a pattern of features that fit a specific chemical composition. The team working with the Kuno et al. 2025 study performed this extraction and found a clear excess in the mid-infrared spectrum above what the companion alone could explain. That excess is the disk signal, and when they examined the spectrum of that disk material, they found carbon-bearing molecules. 7 of them, including molecules that grow more complex than water, methane, or carbon monoxide, all the way up to benzene. Before going further, it helps to understand what the 7 molecules represent structurally. The list starts with relatively simple species and builds in complexity. Small molecules like carbon monoxide contain just 2 atoms. Moving up the complexity ladder, you reach molecules with 3, 4, or more carbon atoms, and eventually reach benzene, a ring of 6 carbon atoms with hydrogen atoms attached at each vertex. Benzene is an aromatic hydrocarbon, and its detection is significant not just because it is complex, but because ring-structured carbon molecules are stepping stones toward larger organic compounds. Interstellar and disk chemistry can build these rings when conditions of temperature, density, and radiation exposure are right. Finding benzene in the disk around CT-CHA-b means the chemistry has progressed to a level of complexity that goes well beyond simple molecules. And finding 7 carbon-bearing molecules simultaneously means the chemistry is not a single isolated process. It is a system, multiple reactions, multiple products, all operating in the same disk environment. Now let's put that in context carefully. Carbon-bearing molecules in a disk are not surprising in principle. We expect chemical complexity in disk environments. The interesting finding here is the variety and richness of carbon-bearing species in the disk around CT-CHA-b, and how it compares to what is seen in the disk around the host star CT-CHA. The disk around CT-CHA, the star itself, does not show the same suite of carbon-bearing molecules in the observed spectrum. The 2 disks, star and companion, appear chemically distinct. The companion's disk appears richer in carbon-bearing species relative to oxygen-bearing species. This is sometimes expressed as a high carbon-to-oxygen ratio, a high C/O ratio, with the gaseous C/O ratio reported as greater than 1 in the disk around CT-CHA-b. To understand why the C/O ratio carries such physical significance, it helps to think about what happens to oxygen in a disk. Oxygen is one of the most reactive elements in a disk environment. It bonds readily with hydrogen to form water, with carbon to form carbon monoxide and carbon dioxide, and with silicon to form silicate minerals. When conditions are cold enough, water freezes onto solid particles. It crosses the water snowline and leaves the gas phase. When this happens, the oxygen tied up in water is no longer available in the gas. What remains in the gas becomes relatively enriched in carbon-bearing species compared to oxygen-bearing ones. So a high C/O ratio in the gas phase, above 1 as reported for the CT-CHA-b disk, is a signature of conditions beyond the water snowline, where water has frozen out and the gas phase oxygen inventory is depleted. The carbon-bearing molecules that Webb detected are the chemical residue of a disk environment where oxygen has preferentially moved into solid particles, leaving the gas relatively carbon-rich, and that difference carries physical meaning. A high C/O ratio does not form randomly. It reflects the history of how the disk material evolved, how temperature changed with distance from the companion, how molecules froze out onto solid particles at different distances, how the solid and gas phases of the disk traded material over time. The fact that the two disks, star and companion, have diverged chemically after just 2 million years suggests that circumplanetary disks can develop their own distinct chemistry relatively quickly. Now, here is the most important statement about what this observation means. Webb characterized chemical and physical properties of material in the disk around CT b. That is what it measured. Material. Disk material. Not a moon, not a body in the process of forming, not a solid object. Gas and possibly fine particles in the disk around a young planetary mass companion. There is one more point worth making about the CT b observations in the context of what the field can now do. For most of the history of planetary science, the chemistry we could study was the chemistry preserved in solid bodies, in meteorites, in lunar rocks, in the spectra of planets and moons. These are the end products of formation, not the process. Webb's ability to characterize gas phase disk chemistry in a young circumplanetary disk is genuinely new territory. It means we can, for the first time at this level of detail, read the chemistry of a moon-building environment while it is still in operation. That is the observational breakthrough here. Not a moon, not a confirmed moon candidate, but the chemical environment in which moons, if they form, will be built. A first characterization of the construction material, and a disk is not a moon. Characterizing a disk is not detecting a moon. This is where we examine exactly what the boundary is. But before we get there, let's hold the positive result clearly. 7 carbon-bearing molecules, a gaseous carbon-to-oxygen ratio estimated above 1, chemistry that diverges sharply from the host star's disk, a system young enough that the disk is still present and active. These are not preliminary hints. They are a direct chemical measurement from material surrounding a planetary mass object, made possible by an instrument that did not exist 5 years ago. The moon formation question now has an observational foothold in the disk condition data. That is the real value of what Webb measured here, regardless of how the boundary questions get resolved. Now, let's think about why the chemistry of a disk matters for the moons that might eventually grow inside it. The material in a circumplanetary disk is not just a bulk mass of rock and ice waiting to be assembled. It is a specific chemical mixture, specific molecules in specific proportions, distributed across the disk at different distances from the planet, existing partly as gas and partly as solid particles depending on temperature. And that specific mixture shapes what any moon that forms inside it can be made of. Think about the moon's composition. The moon is largely dry, it has some water, but far less than Earth. One major reason is that the moon formed from material thrown into orbit by a giant impact, material that had already been processed through the high-temperature conditions of the early Earth. The history of the material determined the composition of the body it built. The same logic applies inside a circumplanetary disk. If the disk is rich in certain carbon-bearing molecules, but relatively poor in water-bearing molecules, any bodies that form inside it will reflect that imbalance. The moons will be carbon-rich. Their surfaces and interiors will carry the chemical signature of the disk that made them. But it is more complicated than just reading a bulk composition. The disk has structure. Temperature decreases with distance from the central planet. Different molecules have different condensation temperatures, the temperature at which they freeze out of the gas phase and become solid particles. Different molecules have different snowlines. Water freezes at around 170 Kelvin in a disk environment. Carbon dioxide freezes at lower temperatures, around 70 to 80 Kelvin. Carbon monoxide freezes at even lower temperatures, around 25 to 35 Kelvin. So as you move outward in a disk, from warm inner regions to cold outer regions, you cross one snowline after another. First the water snowline, where water transitions from vapor to ice. Then the carbon dioxide snowline. Then the carbon monoxide snowline. At each boundary, a different molecule transitions from gas to solid, changing what is available in each form at each distance. These transitions matter for moon composition. A moon forming inside the water snowline, where water is gaseous, will be water poor. It cannot easily collect water ice because none is present as a solid in its orbit. A moon forming outside the water snowline but inside the carbon dioxide snowline will have access to water ice but not carbon dioxide ice. A moon forming in the coldest outer regions of the disk has access to all the ices. The snowline pattern imprinted on the Galilean moons, dry Io, icy Europa, icier Ganymede and Callisto, directly reflects where each one formed relative to the water snowline in Jupiter's circumplanetary disk. Now here is the connection to CT-CHA-b. The disk around CT-CHA-b shows an elevated C/O ratio in the gas phase, more carbon-bearing molecules relative to oxygen-bearing molecules than we see in the host star's disk. That asymmetry tells us something about where the snowlines in the CT-CHA-b disk fall, and about which molecules have condensed onto particles versus remaining in the gas. The elevated C/O ratio we see is consistent with material that has passed the water snowline, where water has condensed onto solid particles, taking its oxygen with it. But what makes the CT-CHA-b disk interesting is that the ratio appears significantly carbon-enriched, not just slightly above unity. This suggests either that the water snowline in the CT-CHA-b disk is at a smaller distance from the companion than it would be in a Jupiter-like disk, meaning more of the disk's volume has carbon-enriched gas, or that the disk has some additional source of carbon enrichment beyond just water condensation. The specific star-forming environment of CT-CHA may have produced a companion disk with a genuinely higher baseline carbon content compared to the early solar system. When water freezes onto solid particles, the oxygen goes with it. What is left in the gas phase becomes relatively carbon-enriched. The 7 carbon-bearing molecules detected by Webb, including benzene, are consistent with this interpretation. We are seeing the gas phase residue of a disk environment where oxygen has been preferentially locked into solid particles rather than remaining in the gas. And here is why that matters for moon formation. A moon forming in the outer region of the CT-CHA-b disk would have access to water ice as a building material. The ice is already frozen onto particles and available, but the body would form in an environment that also has unusual concentrations of carbon-bearing molecules. Its surface and interior would reflect both. If the Galilean moons represent what forms in a relatively water-favorable disk environment, moons around CT-CHA-b might have a different character, more carbon-rich surfaces, potentially different interior compositions. Think about the scientific lever this gives future observers. If we can establish the chemistry of a circumplanetary disk before any moons form, and if those moons eventually form and can be characterized, we can compare the disk chemistry with the moon chemistry. We can test whether the composition of the moons actually reflects the composition of the disk that built them. That kind of test would be extraordinarily valuable for moon formation theory. It would tell us whether the chemical connection between disk and moon is preserved, or whether other processes, differentiation, outgassing, impact mixing, change the composition substantially after formation. CT-CHA-b is too young and the moons too hypothetical to run that comparison today. But the disk chemistry Webb measured is a baseline. We are not predicting specific moons. The disk around CT-CHA-b may or may not produce moons at all, but if it does, the chemistry Webb measured tells us something about what those moons could be made of. And that is a different kind of knowledge from simply knowing that a disk exists. Chemistry differs from place to place and time to time in ways that mass and architecture alone cannot capture. 2 moon systems might have the same number of moons, orbiting at similar distances from similar mass planets. But if they formed in disks with different C/O ratios, different snowline positions, different balances of rock and ice, the moons will be different bodies, with different surface compositions, different interior structures, different possibilities for liquid water or organic chemistry. This is why studying the disk chemistry directly is more than a preparation step. It is a prediction. The chemistry is the preview, and it is also a reminder that when we compare CT-CHA-b to Jupiter, we should be careful not to assume the comparison is exact. Different disks, different compositions, potentially different outcomes. The logic of disk-borne moon formation may be universal, but the details, the specific moons, their specific compositions, those will be shaped by the specific chemistry of each disk. We will return to that distinction when we look more carefully at how the Jupiter analogy works and where it reaches its limits. For now, the key point is this. Webb did not just confirm that a disk exists around CT-CHA-b, it told us something about what that disk is made of. And what a disk is made of is directly connected to what moons it can produce. That is the power of spectroscopy. Not just detection, characterization, and here is what that word means in practice. Detection tells us something is there, a thermal excess, a brightness anomaly, a blob near a star. Characterization tells us what it is made of, what molecules are present, what temperatures they imply, how the chemistry compares to other environments we know. For the moon building question, characterization is what matters most, because it is the chemistry of the disk that determines what kind of moons can form. An oxygen-rich disk builds different moons than a carbon-rich one. A warm inner zone builds different solids than a cold outer region. The spectrum is not a secondary result. It is the result. The Cugno et al. Paper reporting on CT-Cha-B detected 7 carbon-bearing molecules, including benzene, one of the most complex organic molecules, identified in a protoplanetary or circumplanetary disk environment at the time, a gaseous carbon-to-oxygen ratio estimated above 1, and a chemistry that differs sharply from the host star's disk, which lacks the carbon-bearing molecular signatures seen around the companion. These are not just interesting numbers, they describe a chemical environment that has diverged rapidly from its parent system, raising questions about how and why circumplanetary disks can develop such distinct chemistry within just a couple of million years. That is the power of spectroscopy, not just detection, characterization. Now, let's say the cautious part plainly, and let it make the story stronger, not weaker. Webb did not detect a moon around CT-Cha-B. No moon was discovered, no exomoon was confirmed. What was measured was material in a disk, gas phase molecules in the disk atmosphere around a young planetary mass companion. The evidence for moon-forming conditions is significant and genuine. The evidence for a finished moon is not there, and the scientific community has been careful about this. The NASA and STSCI press releases around the CT-Cha-B observations explicitly stated that no moons were detected. The language in the Cugno et al. 2025 paper is precise. The result is a characterization of circumplanetary disk material, not of a moon. That level of institutional and publication-level care is not accidental. It reflects a desire to avoid overclaiming a result that is genuinely valuable and does not need to be overstated to be important. And that boundary is not a disappointment. It is exactly the right description of what the science can and cannot say. Respecting it is what separates careful science communication from the kind of overclaiming that erodes trust in astronomy over time. But let's go further. Even granting that the disk around CT-Cha-B is a real moon-forming environment, we cannot conclude from that alone that moons will form there. The disk is a necessary condition. It is not a sufficient one. Consider the variables that determine whether moons actually grow. First, solid delivery. We saw earlier that moon building requires solids to accumulate inside the disk. Pebbles, ablated fragments from captured planetesimals. Condensed ice. Something has to build up in the solid form. The disk around CT-Cha-B contains gas phase molecules. Whether it contains enough solids in the right locations to seed moon growth is not yet characterized. Second, migration. Even if moons begin to form, they face the inward migration problem we discussed. The disk environment that produces moons also pushes them toward the planet. Whether any given forming body will survive long enough to become a permanent moon depends on the balance between its growth rate and its migration rate, a balance that is controlled by the disk's gas density, its lifetime, and the timing of solid delivery. We cannot measure those properties for the CT-Cha-B disk with current data. Third, disk lifetime. The CT-Cha system is 2 million years old. The disk may survive for another million years, or less, or more. And disk lifetime is connected to the supply. The disk around CT-Cha-B is being fed. Material is still flowing in from the host system at some level, given the youth of the system. But as CT-Cha-B ages and the host protoplanetary disk disperses, the supply of material to the companion's disk will shut off. Once the supply ends, the disk evolves on its own. Gas dissipates through accretion onto the companion, through radiation pressure, through interactions with the interstellar medium. By 10 million years of age, 5 times the current age of CT Chabby, the disk will likely be a fossil at most. Fourth, survival after the disk clears. Even if moons grow to substantial sizes inside the disk, their long-term stability depends on the gravitational environment after the disk disperses. A companion orbiting at 440 astronomical units from its host star may experience gravitational perturbations that do not apply to a Jupiter-like planet much closer in. The final architecture of any moon system around CT Chabby would be shaped by these post-disk dynamics. Now let's widen this to the broader exomoon search, because it is relevant here. Despite decades of searching, no exomoon has been confirmed to date. There are candidates. Kepler 1625 b was reported in 2018 as a candidate Neptune-sized moon around a Jupiter-like planet based on Hubble transit timing data. The candidate was based on a transit timing variation. The planet's transit across the face of its star happened slightly earlier or later than a perfectly regular orbit would predict, suggesting a massive moon was gravitationally tugging on it. Hubble observations also appeared to show a secondary dip in stellar brightness after the planet's transit, consistent with a large moon following the planet out of the transit. But subsequent analysis and additional Kepler data have not confirmed it. The additional dip was shown by some analyses to be within the range of systematic effects. The timing variation was real, but not unambiguous. The candidate has neither been confirmed nor definitively ruled out. It sits in the uncomfortable middle ground of consistent with but not proven by the available data. That is where exomoon science currently lives. Zerlo and collaborators in 2020 work surveying directly imaged companions for evidence of disks or planetary objects, identified what they described as a disk candidate around DH Tauri b, another young wide separation companion with excess emission suggesting some extended material. That candidate also had not been confirmed as a resolved disk with characterized chemistry. The field was, until recently, at the stage of hints and candidates rather than confirmed direct characterizations. CT Chabby is the case that moved the needle. To confirm an exomoon around a wide separation giant planet like CT Chabby, an observer would need to directly image the moon as a separate point of light, or detect it through its gravitational influence on the companion's motion. A moon large enough to be gravitationally interesting, say, a Ganymede-sized body at a similar relative distance from CT Chabby, would reflect or emit a tiny fraction of the light at 165 light-years. Resolving that signal from the companion's own light would require angular resolution and sensitivity significantly beyond what current instruments can achieve for such faint objects at close angular separations. It is not an impossible measurement in principle, but it requires instrumentation beyond what is currently operational. CT Chabby does not change this picture. It moves the evidence one step in a useful direction, from pure inference toward direct disk characterization, but it does not cross the gap from disk to confirmed moon. And here is the important positive framing for that boundary. The fact that we can now characterize disk material chemistry in a circumplanetary disk environment is genuinely new. It means the next generation of observations can move from asking whether disks exist to asking what they contain, how they evolve, and whether the conditions inside them are consistent with moon formation. And what does the broader exomoon search tell us about what is needed? Transit timing variations require precise, long-duration photometric monitoring of the right systems. Future missions designed to find and characterize transiting planets around nearby stars, and to monitor them with sufficient precision over long baselines, could provide the dataset needed to push exomoon detection forward systematically. Each new characterization of a circumplanetary disk adds to the sample. Each comparison between disks builds a picture of what the range of circumplanetary disk chemistry looks like. So the limits on what CT Chabby proves are not failures. They are the honest edge of what this generation of observations can deliver. We are at the beginning of being able to directly study these environments, not at the end. Now, here is why that boundary matters beyond the immediate question of CT Chabby. Every time a result is overclaimed in science, there is a cost. The overclaim generates attention, but it also generates skepticism when the stronger version of the claim cannot be verified. And in a field where progress depends on carefully building a case from accumulating observations, premature certainty is genuinely damaging. The practical isolation thesis that a disk is a moon-forming environment but is not itself a confirmed moon is not a limitation of the result, it is the correct description of it. The disk chemistry says the right ingredients are present in a plausible arrangement at the right age for active construction. The absence of a detected moon says construction may be underway or may have already produced objects below our current detection threshold. Both statements are true, and both are useful. What would upgrade the result is either direct detection of a moon mass object in the system, or a chemical signature so specific to moon-forming processes that it implies active accretion onto growing lunar bodies. Neither of those is yet in hand, but neither is ruled out, and the trajectory of the field, from something is there to this is what the disk contains, suggests that the next step is achievable with continued observation. We are at the beginning of being able to directly study these environments, not at the end. Now, let's be precise about what the CT-CHA-B comparison with Jupiter can and cannot carry. It can carry the broad mechanism. Giant planets can form circumplanetary disks. Those disks can serve as moon-building environments. The physics of angular momentum, disk formation, and disk-driven accretion applies across a wide range of planet masses and formation environments. In that sense, CT-CHA-B is telling us that the same basic story is plausible in other systems, but CT-CHA-B is not the early solar system replayed. Let's look at the differences clearly. Mass is the first difference. CT-CHA-B has an estimated mass of roughly 17 Jupiter masses. Jupiter itself is by definition one Jupiter mass. At 17 Jupiter masses, CT-CHA-B sits in a regime where different physical processes may be at work than at Jupiter's mass. A more massive companion has a deeper gravitational potential well, which affects how gas flows into the circumplanetary disk, how quickly material settles, and what the disk's temperature profile looks like. The ratio of the companion's mass to the host star's mass is also different. CT-CHA's star is roughly comparable to the Sun, so CT-CHA-B is a much larger fraction of the total system mass than Jupiter is in our solar system. More massive central bodies also tend to produce more massive disks, because the gravitational influence extends farther and captures a larger share of the infalling material. If CT-CHA-B's disk is more massive than a Jupiter analog disk would be, the moon-building conditions might be richer in raw material, but the migration environment could also be more hostile. A more massive disk means stronger disk torques on forming moons. Separation is the second difference. CT-CHA-B orbits about 440 astronomical units from its host star. Jupiter orbits about 5.2 astronomical units from the Sun. The environment that shaped Jupiter's circumplanetary disk, including the temperature of the surrounding nebula, the flux of material from the protoplanetary disk, and the gravitational influence of the inner solar system, was very different from the environment shaping the CT-CHA-B disk at 440 astronomical units. At Jupiter's distance, the circumjovian disk was fed by material streaming in from the solar nebula, with infall geometry shaped by the nebula's density and temperature profile at that distance. At 440 astronomical units, CT-CHA-B is so far from the star that it is barely within the edge of a typical protoplanetary disk structure. The material feeding the CT-CHA-B disk may be coming primarily from the residual material in the outer protoplanetary disk, from infall from the surrounding molecular cloud, or through some combination. The feeding mechanism at this separation is less well understood than the feeding mechanism for a close-in giant planet, and that matters for what the disk looks like and how long it persists. The chemistry is a third difference. We have already seen that the disk around CT-CHA-B shows a carbon-rich chemical profile different from both the host star disk and from what we infer about the early Jovian disk. The Galilean moons show a compositional gradient that implies the water snow line fell between Io and Europa. The CT-CHA-B disk chemistry suggests a different balance of ices and carbon compounds, which could produce moons with different compositions if moons form at all, and the age comparison requires care. CT-CHA-B is roughly 2 million years old. Jupiter was fully formed within the first few million years of the solar system, so in developmental terms the comparison is roughly contemporaneous. But the environment that Jupiter formed in was shaped by the presence of rocky planets already forming in the inner regions, the dynamics of the Sun's early evolution, and the specific thermal and compositional structure of the solar nebula. None of those specifics apply to CT-Cha-B, so what is the analogy good for? It is good for testing the basic mechanism. Does a giant planet-scale object produce a circumplanetary disk? CT-Cha-B says yes. Can we observe disk material directly in a young enough system? CT-Cha-B says yes. Does the disk chemistry in a planet-centered disk evolve differently from the chemistry in the surrounding host star disk? CT-Cha-B says yes, and quickly. Those are real confirmations. They support the broad theory that disk-borne moon formation is not unique to our solar system. They give us a case study outside our own history. But we should hold the analogy at the level where it is valid. Jupiter and CT-Cha-B are not the same system. They are two instances of a class, giant planets with circumplanetary disks at formation-relevant ages. The class exists. The two members have shared physics and distinct histories. Think about what questions the variation between them can eventually answer. If circumplanetary disks with high C/O ratios tend to produce carbon-rich moon systems, and disks with lower C/O ratios produce more water-rich systems, like the Galilean moons, that relationship, if confirmed across multiple systems, becomes a predictive tool. We could look at a disk chemistry measurement and make a prediction about the character of the moon system it would produce. CT-Cha-B, as our first well-characterized case outside the solar system, is where that project begins. And actually, that is more useful for science than a perfect copy would be. If every giant planet produced an identical disk with identical outcomes, there would be nothing to compare. The interesting science lives in the variation, in understanding why different systems produce different outcomes, what the controlling variables are, and what range of moon architectures is possible across the galaxy. Science does not build understanding from single examples. A single moon system, even as well studied as Jupiter's, tells us one successful outcome, but not the range of possible outcomes. CT-Cha-B gives us a comparison. What is the same between these two cases? What is different? Which differences produce which outcomes? CT-Cha-B gives us a second data point. And a second data point is what begins to turn a single example into a sample. Now think about what further data points would tell us if the next young wide separation companion with a circumplanetary disk shows similar carbon-rich chemistry. We would have grounds to ask whether this is a common feature of circumplanetary disk environments or a peculiarity of CT-Cha-B's specific conditions. If the next system shows a different chemistry, perhaps oxygen-rich rather than carbon-rich, we learn something about the variation space. Either outcome is scientifically useful. Consistency narrows the model, variation expands it and adds new questions about what drives the differences. And there is a deeper value to the Jupiter-CT-Cha-B comparison that goes beyond the specific chemistry. The fact that a young planetary mass companion at a very different mass and separation than Jupiter is still producing a disk with moon-forming ingredients tells us something general. The conditions for circumplanetary disk formation are not exquisitely fine-tuned. They appear over a range of companion masses and separations. That generality, if confirmed by more observations, would support the idea that disk-built moon systems are a common outcome of giant planet formation rather than a special coincidence that happened to produce our Galilean neighbors. Jupiter is the bridge in the sense that it gives us the outcome to measure against. CT-Cha-B is the bridge in the sense that it gives us the process to observe directly. Neither one alone closes the argument. Together, they begin to outline the shape of a complete picture. So what would make that picture sharper? More systems, more young planetary mass companions with circumplanetary disk detections, ideally a range of masses, separations, and host star environments that lets us see whether disk chemistry is consistent across giant planet analogues, or whether it varies in ways that connect to the kind of moon systems that eventually form. And ultimately, direct detection of moon mass objects around at least one such companion, not inferred from disk chemistry, but directly resolved. None of those observations are in hand yet. But the trajectory is clear. CT-Cha-B moved the field from indirect inference to direct chemical characterization. The next step moves from characterization to detection, and the step after that connects detection back to the full architecture question. Are disk-built moon systems a natural outcome of giant planet formation, or are they one of several possible paths with different frequencies? We will not have the answer to how common moon systems are just from CT-CHA-b. But we are beginning to build the set of observations that could eventually answer that question. Now, let's ask the question this video has been building toward. If giant planets can build disks, and disks can build moons, how common are moon systems in the galaxy? The honest answer is that we do not yet know, but we can say something more useful than that, because we know the argument chain is plausible, and we know where the uncertainty sits at each link. Start with what seems likely based on current knowledge. Giant planets appear to be relatively common. Radial velocity surveys, which detect planets through the wobble they cause in a star's motion, have found that roughly 10 to 20% of Sun-like stars host a Jupiter mass or larger planet within a few astronomical units. Kepler's transit survey found giant planets to be rarer among close-in orbits than ground-based surveys initially suggested. But wide-orbit giants are harder to detect with transits, and their frequency is less well constrained. The overall picture is that gas giants are not exceptional features of rare planetary systems. They are moderately common, less common than smaller rocky or ice giant planets, but present across a significant fraction of stellar systems. If that fraction is even roughly correct, the galaxy contains an enormous number of giant planets that formed or are forming with circumplanetary disks. The question of what fraction of those disks produce surviving moon systems is a question about a large absolute number of objects. If giant planets are common, and if disk formation around a growing giant planet is a natural consequence of the same physics that forms disks around growing stars, then circumplanetary disks should also be common, at least in systems with giant planets, and at least during the early formation phase. And if circumplanetary disks are common, moon-building conditions should be common too. But here we have to be careful. Common conditions do not guarantee common outcomes. The same variability that applies to planet formation from protoplanetary disks also likely applies to moon formation from circumplanetary disks. There is also a question of what we mean by moon system. A gas giant that produced one large moon and several smaller irregular ones is very different from a gas giant that produced 4 large regular moons in a resonant chain. If the Galilean configuration is the result of a particular set of disk conditions, gas-starved, slowly supplied, with the right solid-to-gas ratio and the right disk lifetime, then not every giant planet will produce a Galilean analog. Some may produce a single large moon. Some may produce multiple smaller moons. Some may produce conditions technically favorable for moon building, but lose every generation of forming moons to migration before the disk dissipates. The range of possible outcomes from circumplanetary disk physics is probably as wide as the range of possible outcomes from protoplanetary disk physics. This variability is not a weakness in the theory. It is a prediction that can eventually be tested. As our sample of observed circumplanetary disks grows, and as exo-moon detection technology matures, we will begin to see whether the predicted variability in moon system architecture is actually present in the population of giant exoplanets. Now, what does CT-CHA-b change in that picture? It moves us from pure inference to one concrete observational case. Before observations like the CT-CHA-b Webb data, the case for circumplanetary disks rested almost entirely on the evidence of moon systems we already had in our solar system plus theoretical models. CT-CHA-b gives us a case where a disk exists and can be characterized independently of a moon system. It exists in a different system around a different kind of object, with different chemistry, and it still looks like a disk-borne moon formation environment. That second data point strengthens the argument that circumplanetary disks are not a special feature of our solar system. And the direction of travel matters here. Liu and collaborators in 2024 specifically modeled what future JWST observations could do for characterizing disks around a broader sample of planetary mass companions. Their work showed that comparing the near to mid-infrared colors of these objects, essentially measuring the ratio of brightness at different wavelengths, can help distinguish objects with significant disk material from those without, and distinguish different disks' geometries and temperatures, That kind of photometric characterization can be done for more targets than spectroscopy can because it requires less total observing time per target. It could be used to identify which wide separation companions are the most disk-rich, making them the best targets for more expensive and detailed spectroscopic follow-up. Over the course of Webb's operational lifetime, this approach could turn our sample of characterized circumplanetary disks from 1 CT-CHA-b into tens or potentially more. Webb has now shown that mid-infrared spectroscopy can characterize disk material around young wide separation companions. That means we can do this measurement again. There are other wide separation companions in young star-forming regions. There are other systems at the right age and the right separation to be observed with similar techniques. Each new characterization adds to the sample. Each comparison between disks in different systems at different ages with different host stars builds a picture of what the range of circumplanetary disk chemistry looks like, and eventually, better instruments will push the observations closer in. The planned generation of extremely large ground-based telescopes, instruments with primary mirror diameters of 30 to 40 meters compared to the 8 to 10 meter class of current large telescopes, will have angular resolution in the near-infrared that exceeds what current observatories can achieve. At that resolution, the angular separation between a giant planet and its largest moon, in a suitably close and well-positioned nearby young system, could become resolvable. The path to confirmed exomoon detection does not run only through space telescopes. It also runs through the next generation of adaptive optics-equipped ground-based observatories. And when that confirmation comes, when the first exomoon is definitively resolved or detected through its gravitational and spectroscopic signatures, it will arrive against a backdrop of disk chemistry measurements. The moon will not be a complete surprise. We will already have some sense of what the disk that made it contained, whether the chemistry is consistent with the observed moon's inferred composition, and how the system compares to others we have studied. That interpretive context is what the current generation of observations is building. So we are building the scaffolding for a question the next generation of instruments will begin to answer. And the scaffolding rests on a reframing that everything in this video has been building toward. Moons are not afterthoughts. They are the architecture left behind by formation. When we understand the disk, we understand the moon system it could have produced. When we understand the moon system, we are reading back the history of the disk, and that two-way reading has implications that extend beyond our solar system. Every exoplanet system we detect is itself a moon system in waiting, or a moon system already built around planets we cannot yet resolve. The giant planets we catalogue around other stars may each carry families of large regular moons, assembled in circumplanetary disks during formation, carrying chemical fingerprints of the conditions that existed when those planets were young. We cannot see those moons yet. The instruments and methods for direct exomoon detection are still in their infancy, and confirmed exomoons remain elusive. But the theoretical expectation, grounded in the Galilean system and beginning to be tested by observations like CT-CHA-b, is that they are there, that the moon-building process is not unique to our solar system, that wherever a giant planet formed with enough infalling material to sustain a circumplanetary disk, moons likely followed. The question of how common moon systems are is therefore also a question about how common disk-forming giant planets are, and about how readily the disk-to-moon pipeline operates across a range of stellar environments, disk compositions, and formation timescales. Those are questions that will take many more observations to answer, but they are questions that now have an observational foothold they did not have before. Giant planets are not simply planets with satellites. Under the right conditions, they are small centers of construction that organize the material around them into ordered families of worlds. That is what Jupiter's moons are. That is what the disk around CT-CHA-b may one day become. And that is why the question of how common moon systems are is really a question about how common giant planet formation is, and about what it means to be a planet in the first place. And we are in a position, for the first time, to actually begin observing the answer. Not inferring it from finished architecture alone, not modeling it from first principles without any direct measurement, but reading it in the chemistry of material around young planetary mass objects, in the disk signals that Webb and its successors will accumulate across more systems, and eventually in the detection of the moons themselves. The machinery of moon formation is no longer invisible. We are beginning to watch it run. Now, let's return to the question we opened with. Where do big moons around giant planets actually come from? The answer the evidence gives us is this. Large regular moons, the kind arranged in orderly families around giant planets, most likely grow inside disks of material that form around those planets while they are still growing. The physics that builds them is the same physics that builds planets themselves: angular momentum, accretion, the slow gathering of diffuse material into organized structure, but operating at a smaller scale around a smaller center of gravity. Jupiter's Galilean moons are the nearest example we have. Their flat orbits, their resonant rhythms, their compositional gradient from dry Io to icy Callisto, all of it points back to a disk that once surrounded young Jupiter and is now long gone. The moons are the record it left behind. CT Chabé lets us study something like that disk while it still exists, at another star, around another kind of object, in a system only 2 million years old. Webb's MIRI measured the chemistry of material in the disk around CT Chabé. It found 7 carbon-bearing molecules, a chemical profile distinct from the host star's disk, and evidence of rapid chemical evolution in a planet-centered environment. Not a moon, not a confirmed moon in progress, but the material from which moons of a specific character could, under the right conditions, eventually grow. And the boundary between those two things, disk material and finished moon, is exactly where the science currently stands. We can now observe the environment. We cannot yet watch the outcome. But that is a different kind of uncertainty from the uncertainty we had before. We are no longer inferring disks entirely from their products. We are beginning to observe them directly, read their chemistry, compare them across systems, and build the observational base that will eventually let us test whether moon formation follows from disk formation as reliably as we believe it does. The picture that emerges is not small. Planets are not just planets. Under the right conditions, a mass large enough, a disk present long enough, material delivered in the right form, a planet becomes a local center of construction. It gathers material, it organizes it, it produces structure at a smaller scale than the star system around it, a miniature architecture nested inside the larger one. And those miniature architectures, the moon systems, are not decorations. They are records of formation. Every regular moon is a frozen clue about what the disk that made it looked like, what its chemistry was, what its temperature structure was, how long it survived. We are learning, slowly, to read those clues. And what we are finding is that the universe has been doing this kind of construction, systems inside systems, orbits inside orbits, with a consistency that tells us the underlying physics is robust. Giant planets build their own moons. Not always, not guaranteed, not in every case, but where the conditions allow it, the process unfolds. And the moons that survive to tell the story are among the most physically informative objects in the galaxy. Jupiter showed us the pattern. CT Chabé showed us the process. And that combination, outcome plus ongoing construction, is what turns a long-standing inference into something we are beginning to directly observe. The question that started with 4 moons in orderly orbits around our largest neighbor now has a live system to point to. The machinery is no longer hidden inside 4 billion years of solar system history. We can watch it, read its chemistry, and ask what it will leave behind.